Okay, you can continue. I will come back to this to understand something. I will come back to this simple. Okay, to understand this behavior, I mean analytically. You know, the best way to, when you have a differential or partial differential equation, or as you like, is to look for exponential solutions to understand what happens. Exponential solutions with complex coefficients. Okay, let's look for solutions of this form with u of 0, different 0, not to have a trivial solution, so a solution, of course, and lambda a complex number. Then if we put this here, we will have lambda, exponential lambda t equals, or I will put plus exponential lambda t minus tau equals to 0. I can take the exponential because it's positive, and u0 is real or complex. It's not important. Then we have, if we want to find the solutions of this form, we have to find coefficients satisfying this expression. We can take here the exponential, and we will have, and also u, and we'll have lambda plus exponential lambda minus lambda tau equals to 0. If we are able to solve this equation, we will have lambda and have solution. The problem, they have infinite many solutions. This is the difference between ordinary, because we are looking for complex. If you put cosine and sine, you will see that it's impossible to solve. But to have oscillations in general means that there is a complex. If you want only oscillations, you have to prove that there is complex solution. Okay, let's start by real solution. If we can find a real solution of this. Yes, of course. Yes, yes. This is exactly what. For example, this one, there is a limit cycle of period p over 2. And the limit cycle becomes bigger. Yes. After, when you take tau greater than pi over 2, you have a limit cycle. I think with period 4. 4 times tau. And the limit cycle is attractive because in general, when I say there is periodic solution, it's not exactly this. There is periodic solutions that attracts all the others. Because as we start with initial conditions not periodic, like constant, after a certain time, this solution will go to a periodic cycle. And we can, I think the limit cycle that we have here is a 2-dimension. We have 2-dimension limit cycle. Yes. And we can prove it. This is a Hopf verification theorem that I will show you after. You're welcome. Okay, there is nothing. Okay, I will solve this. Maybe I put it here, and it's like lambda exponential lambda tau, or tau lambda, equals to -1, no? Or +1 equals. I will put +1 equals to 0. First, let's start by real solutions. If we can find real solutions, let's take this like a function from R to R. Can we have a real? Yes, okay, this is derivative. It's exponential tau lambda 1 plus tau. It's always positive. Then it's tau. Yes, it's always positive because we not always, because it depends on tau, on lambda, derivative of this tau. This is true, and the limit, if lambda go to minus infinity, this is 0. Then it go to 1. Maybe I will put one other part like that. It go to 0, and the limit 1 lambda go to plus infinity is plus infinity, and he has this form. And there is delta lambda equals to 0. It's lambda equals minus 1 over tau. Okay, then I have to compute delta of minus 1 over tau. If I put it here, it's minus 1 over tau, and this, and minus 1. This is true? Yes. And it's negative. That means for this point, we have over tau. It's the minimum. And the function go to 0, and here go to plus infinity. I have to calculate for lambda equals to 0. For lambda, it's 0. And 1 lambda go to plus infinity, it goes to plus infinity. It has this form. Okay, and we want to solve this equals to minus 1. And you see the limit. If we, because this minimum, it's exactly this one. Okay, this is the minimum here. And we want to solve the equation with minus 1. Then we increase tau. It means that we'll go up. If we decrease, we have this. And the limit to have like to be here is to take tau equals to minus tau minus 1 over tau exponential equals to minus 1. And what is tau that give you this limit? Which value of tau give you minus 1? When you increase tau, becomes decrease until you reach this limit, okay, to have the intersection. And what is the value of tau that gives this limit? Yes, 1 over a. This is what this magic number appears. Appears here. This is why this limit appear, because when tau is less than this value, you have no solution, no real solution. That means only when tau is bigger than this value, you have no real solution. That means all the solutions that we have are complex. That means all the solutions oscillate. This is why we have this behavior. And of course, we can continue to look for imaginary root, and I will do it after for general case. and find this pi over 2. But it's only a complex variable, and there is nothing's very complicated. The equation is very beautiful because we can have many things, and to do it is very easy. It's not complicated. Now I will do it for this, because I told you that all the expressions of the Ley differential equation are equivalent. We can pass from one to another one. I choose this one. After that, I will give a result for the other one or for more general one. In order to, I didn't prove this, but I will do it after, because we can say why for this new equation, we can say that the exponential solutions determine the behavior of the general solution. This we can prove. I will prove it after. In order to determine the solutions, the stability of the trivial steady state of linear delay equation, I will do as for ordinary differential equation. That means we look for lambda for exponential solutions. Then if you consider this, we introduce this linear mapping, because I want to do more than that. And if we note exponential of lambda point this function, okay, and we apply the operator L to this one, we have this. It's exactly the same. This is another way to write it. It's exactly the same. Then we can make simplification for x and this exponential, and then we can say that because I put this operator exactly, the equation here equals to 0. That means to find exponential solutions, we have to find to solve this equals to 0. Okay. At the end, by making all the simplifications, this will be equals to 0 if and only if this functions is equal to 0. It's exactly the same here. Here we have tau equals to 1 and beta equals to 1. Beta equals to 1 here, and tau equals to 1 in the other part. Okay. Do you know what that means? Analytic function. This is very important, because the analytic function is like, what is the analytic function? I will explain after. And as this function is, and this is all the time true for the Ley differential equation. What we will call after characteristic equation, this one will be all the time analytic. What that means analytic? It's also, that means it's entire function. What that means entire, we can develop it in entire Taylor function. But be careful, because I put here like, this is very good to remember all the time what that means. An analytic function is complex function from C to C. We say that it's analytic if and only if it's differentiable for each point in the. Here we will talk about all the space complex. It will be analytic if and only if we have this. Okay. This is the definition of analytic function. Why I insist for this? Because all things that I will do after or delay will be the same. If the characteristic equation is analytic, we have the same results. We don't need to check all the time if there is a. And it is important because as we have infinite number of solutions, it's very important to know this result. I will ask a question. If I take h of z, like complex equals only x, the real part. Is this function analytic? Take only x, or it's not analytic. This is a big mistake because analytic is a very specific function. If you start to do this, you will not be able to. If you make like limit, I will take, for example, limit when z go to 0 of h of z minus h of 0 over z minus 0. The limit. This is x plus ey. This is, sorry, x. Yes. This is 0. And this is x plus. And if I put divide by x, 1. And we can see that this limit can, for example, if you take, no, maybe I make a mistake. It's not the good, this is analytic. No, it's not this one. Because we divide by x. No, sorry, it's not analytic. It's not analytic because if we, the complex z go to 0, that means x and y go to 0 in the same time. If we take x equal y, because we can choose, we have, in that way, you will have 1 over 1 plus a, like limit. And if we take another direction, y equals to x, you will have 1 over 1 plus 2a, and two different limits. It's not possible. That means the limit doesn't exist. That means this function is not analytic. It's not differentiable. This is mistake because if a function is differentiable in R, it doesn't mean it's differentiable in C. That means this notion is more strong than differentiable function in C, because you have to put the real part and imaginary part in the same time, going in the same direction. This is why it's completely different things that what. And yes, why I want to insist for this. If you have an analytic function, that means it's differentiable. We can prove that it's infinitely differentiable. If it's differentiable once, it becomes indifferentiable infinitely. For complex functions, you know why. This is important also. You know that when you have a complex variable, you can make equivalence between. Okay, but the notion of analytic doesn't work here, because for the denominator you have z minus z0 vector. If you put vector, it has no meaning, because you cannot divide by couple x minus xy minus 0, for example. This is why the both notion is completely different. When you have an analytic function, it's infinitely differentiable, and it's always has this development. Okay, you can write it like this for any function. And we have also, if h is an entire function, that means if it's analytic, that means it's entire function. Then the number of 0 of this function, that means solving this, the number of roots of this function is at most it can be finite, but in almost all the time they are countable. That means you have many, but you can make them like a sequence in complex number. And if an entire function has infinitely many different zeros, all the time this this property. And this is very important because we can, this is a general for all analytic functions. We have this result. And as our function lambda, I forget it, it's lambda plus beta minus lambda equals 0. This function, we can prove that it's analytic. That means it's entire, and we have all this property. If there is a root, they satisfy all the time this assumption. That means if you put, this is the complex plan. If you have a root, they will of these roots they will go like this to plus infinity. They cannot have accumulation point. They cannot go, the limit of this will never be finite. That means you will not have accumulation of points near one point. This is very important because we can isolate, you will see. After that, when you put something like this, we are sure that the number of eigenvalue is finite. Because if they are infinite, as they have to go to, something like that. If they have to go to plus infinity, this is contradiction. Then it's important. And this is true for all delay differential system. We have all the time analyticity. Then we conclude all this for this function, but it will be general. I will show you after. If we are looking for a lambda complex solution of this, the set of the roots of this function have cannot have accumulation points. That means we will never have like infinite roots in a bounded domain. This is important. Second, if we take any vertical, this we can prove also. If you put line, take a region like this, you will have only finite number of roots in this region between R1 and R2 for all value. The number of roots are at most countable, and we have also this, and we have also this property, very important. This is very easy to prove. We take this and assume that we have solutions, then you will have this. Okay, and you take modulus, then you have, and this you take real part and imaginary part, and you will have here minus real part, and imaginary part modulus is 1. Okay, and if this go to plus infinity, that means this will go to plus infinity. That means this will go to minus infinity. Okay, it's very easy to prove. This will go to minus infinity. This is important. That means if you have an infinite number of eigenvalue, the real part will go to, they will have accumulation in minus infinity and not in plus infinity. And I will show you that it's very, very interesting, very important, give very things interesting for delay differential. And at the same time, as we have this property, all the eigenvalue will go to minus infinity. That means if you choose any constant m, you take this set, you look for eigenvalue on the right, you will find all the time there is finite number. Okay, only the infinite number is on the left all the time. You put as you like, you will have a finite and finite number. Why it is interesting? Because I think all of you already, when you study ordinary differential equation, I will remember you, ordinary differential system, you take matrix, you look for eigenvalue. Okay, you have eigenvalue, and you look for eigenspace. You remember this? and you say what is eigenspace? It's the space generated by solutions, exponential solutions that come from the eigenvalue. And you have this direct sum between spaces, okay? And you can split your system and solve it in each eigenspace. And the solution will be the sum of this all the solution. Here we have the same. We can do the same. We take eigenvalue, and as we know that on the right we have a finite number of eigenvalue. That means if we take any limit, any axis, and we generate solutions, but by the exponential that are given by, let's say, real part positive of eigenvalue, as they are finite, they will generate ordinary system. And on the left, the difficult part will be generated by infinite number of eigenvalue, but as they will go to minus infinity, they will be negative, and they will give you stability of the system, because we know that if real part of the eigenvalue is negative, the system, then this will make delay differential system very easy to study. You split it in two parts. The difficult part, we know that it will give you stability, and the other part, it will give you finite ordinary differential, because you have a finite number of eigenvalue. We have also this property: if you have a root of this, the conjugate also is a root. I want to come back to this because it's the main part of delay differential system. What I am talking here is about a simple one, can be generalized to all the others. I will come back to this because it's the only thing that we have to know, it's for ordinary differential, the same idea. Let's say we know this property, okay? And this is my complex plan. I know that if I take this, if I choose like vertical axis, I have a finite number of solutions of this on the right. What I will do, I will choose exactly this one as my axis. I know that here I have a finite number of eigenvalue, and they are, I have this property, they are always symmetric. One here, I don't know, one here. And all the others, they are like accumulate in minus infinity. Okay? Now I take all this eigenvalue, I don't know how much. Let's say lambda 1, lambda 2, lambda 3. Okay, let's say I will do better than that, because I will say that I have only two. I choose this to have only two. Okay, lambda 1 and lambda 2. And all the others are on the left. I generate solutions from this. And I generate the eigenspace. Suppose the eigenspace, I will not it like X. What happens in this? And all the others, they are infinite. They will generate space Y. What I know exactly as for ordinary differential equation, the space that I am working on, state space, see, is X plus Y. Each initial condition I took here, I can write it like phi1 plus phi2, unique decomposition. If I take this initial condition, I can solve my system in this space. If I take this initial condition, I will solve my system in this space. This initial condition, as I have here finite dimension space, it will give you a system of dimension exactly 2. And the other one is on the right of this. the eigenvalue in this system will be, the real part will be negative. That means stable. If I take now the solution, general solution, I have the same. It will be x1 coming from x1 coming from this, and x1 and x2 coming from this. Assume that the two eigenvalues that I choose here, this is exactly what will happen after. It's exactly these two. And we know that this solution gives you cosine and sine, periodic solution. That means all the solutions that are here are periodic, with period given by, okay? And this one will go to 0, because it is generated by eigenvalue with negative real parts. But now the solution will go here, because this one go to 0. That means all the solutions will go to the limit cycle, given by this expression. It is of dimension 2, because I choose the eigenvalue exactly what I want to have this. And after that, we will do it correctly analytically by moving beta until we have only these two eigenvalue, and all the others have a negative real parts. In that case, we can, our solution will be limit cycle plus solutions that go to 0. That means when you take t go to plus infinity and you make difference, this minus this, you will have 0. That means all the solutions will go to the periodic solution and limit cycle. This is the way. It's very easy to. After that, of course, you have to. Yes. This is exactly Hopf bifurcation. This is, I put it only for linear system. Hopf bifurcation told you if you have a non-linear system and you make linearization around, you obtain linear system that give you this, you will have the same behavior for the non-linear system. And this is what we call Hopf bifurcation. You move your parameter until you met this two eigen value with imaginary root, and you have, of course, you have this. Oh, this is only to say that if you have a root, they have they are all the time of finite order. You cannot. That means when you make derivative, you will have 0 for certain m. I repeat, this is happens all the time for delay differential system. We have the same property. Also, for distributed delay, almost the same. But this behavior on the right, finite, on the left, infinite, it's all the time happen. Okay, now I move more. I take again this characteristic. I call it now characteristic equation. That means give you stability, periodic solutions, like as in ordinary. And it's exactly what happens. We can prove it. We look for, now we know that we have infinite number, but we want to look for them more by hands. Okay. If we put x, the real part, and y, the imaginary part, then we can write the system like this. X equals to minus beta exponential x, etc., and y like this. And if we look, this is, I already did it for -1. We can do it also for when we have here beta. You can see that, let's start by considering the real roots. Okay, that means y equals to 0 and lambda equals to x. Then our equation becomes like this. This we know the behavior. If beta is negative, that means this is positive. That means there is a unique real root, and this it's positive because if this is positive, that means there is a positive solution, real. Here we stop. That means the equilibrium is unstable because we find a positive eigenvalue. Now, if beta is positive, this is what we call negative feedback. When beta is positive, that means because you have already minus beta in the equation. In that case, it's very interesting. If beta is positive, as you have negative feedback, we can go more. And we can prove this result. Exactly the exponential -1 that I told you comes from this. If beta is between 0 and 1 over exponential, then there is 2 real roots. I already show you because you have, I think, this behavior, something like that. And here we will have 2 real roots and they have negative. If beta is negative, then there is 2 real roots, x1, x negative. And if beta is 1 over e, you are in this limit. You are in this limit, and you have only 1 real root, which is also negative with multiplicity 2. And if beta is greater than 1 over exponential, there is no real roots. This is oscillations. You have all the time. There is one thing. When I say oscillations, that means all the solutions oscillate, all the solutions. If I say nothing, that means maybe there is 1 or 2, but I know there is others doesn't oscillate. Okay, this is the notion of oscillation. If beta is greater than 1 over e, then all non-trivial solutions oscillate. No, this is, I already did. It's very easy to prove. Now we will go more. Now if, because we stop between 0 and 1 over e, now we go until this threshold. In that case, we can prove that there exists, I will prove it after. There exists delta positive such that exactly what I said here, the real part of lambda is less than this negative number. And this for all roots lambda. That means as all roots has less than this value, that means all of them has a negative real part. That means the 0 is asymptotically stable. Okay, if beta is less than this number, we have a local asymptotic stability of 0. That means all the solutions go to 0. And we can complete because this number and the other one is, I think here, it's less than pi over 2. That means between 0 and 1 over e, you have no oscillations, but you go to 0. And between 1 over e and pi over 2, you have in the same time oscillations, but the solutions will go to 0. You have asymptotic stability and oscillations in the same time. And if beta equals to this number, this is exactly what I took here because I know this result, then you will have 2 periodic solutions. But if we use decomposition, etc., these 2 periodic solutions will be attract all the other solutions. And the periodic solutions are generated by this 2 functions. You can put like it's circle. What else? And if now if we go more than this, first 0 will be unstable, but we will have a limit cycle growing all the time. And we can be more precise. This is very interesting also because this is why delay difference give you many things. We prove that if beta is greater than this value, all roots has this form with x positive. This is we know because they are symmetric. But y is between p over 2 and pi over 2. This is give you the periodic of the solution. That means the period of the solution will never be greater than pi. It will be between, even if you put beta go to plus infinity, you will have periodic solutions, but you will have like a limit of periodic solution. They will grow, but after that they will stop by 2 thresholds. And this is very beautiful result to prove because this gives you the period of the solutions, okay? And has a limit between start here, pi over 2, but never pass through this threshold. This is a part of the proof. I will not prove everything, but it's only to show you how it works. First, we can remark that because we solve this system, okay? If xy is a solution, also x minus y is a solution. Then we will not look for xy, x minus y. We will suppose that y is positive and look only for xy. Okay, if we have xy, we will have x minus y. Then we suppose y positive. If we are in the case of beta positive, if beta is positive, if there is a root xy with x positive and y positive, as we restrict this, then we can see that we have this property. It's very easy to see because as beta is positive, you can yes, as x is positive, cosine is negative. Okay, is the first equation of the system give you this property, and the second one give you the fact that sine is positive, cosine positive, and sine y cannot be equals to 0 because if you put y equals to 0 in the system, it doesn't work. Okay, the first equation doesn't give you. This is why we take y greater than 0. And if you, what is which part of the plan you have this? Sine positive and sine positive and cosine negative. Then you are here, and you, as sine of y is strictly positive, you will not take this, and that means you will stay between pi over 2 and pi, but don't take pi because sine will be 0, and as the periodicity we will be here, and periodicity come back to the same. Okay, because sine positive and cosine negative. Then the solution will be in this space. As we are in this space, now you can divide by y because it's, and you transform the second equation of the system to this. Okay. If we calculate the derivative of this function, we have, it's easy. We can see that it is negative because cosine is negative and sine positive. Then this is negative. That means this function is decreasing. That means the maximum is on this point. Okay, as it's decreasing, the maximum, this point, this is why the maximum is for y equals pi over 2. And then we have, yes, for this point, you have also this. Then the maximum of this function, as it's decreasing, it's the first point, it's exactly 2 over pi, the maximum of this function. As the maximum is this point, that means this has to be less than this value, 2 over pi. Okay? And this will give you pi over 2 for all things is related to this. Exponential minus 1 and pi, exactly using this cosine and sine. And as x is positive, then you have this. And the other part, you have the maximum. That means beta has to be greater than pi over 2. And I can tell you all the delay differentiable has the same techniques. It's only very small techniques about cosine. There is no theory, big theory about, because we know already that it works. It's only to check and to find the parameter that give you threshold. This is then we have beta has to be greater than pi over 2. And we can conclude, if we don't have this, that means x is negative, because we assume that x is positive. In the other side now, if if you don't want to have positive real part, we have to not to choose this, but to be outside. Then between 0 and pi over 2, all the solution satisfy this. That means we have a stability of 0. For every roots, that means there exists, because as all of them has real part, and we know that there is finite number on the left, we can then we can prove that there exists delta such that all the real part is less than minus delta, and we have a stability for this for beta between 0 and pi over 2. I can do all the proof, but it's exactly the same techniques. After that, for beta equals, this is very easy. We can only prove that we have two solutions. And for beta greater than, this is more complicated, but it's using only complex number. There is no theory. The same techniques, you prove that pi is between this value and this value. Then we can this we prove it for this for this equation, but we can, as I already told you, that we can pass from one to another by change of parameters. We do it quickly, and we can generate another results for this one. If we take here, instead of 1, take r. Delay, you have the same. If alpha is negative, u is unstable. Now, instead of beta is r alpha. If r alpha is between 0 and pi over 2, you have local asymptotic stability. And if you have this, you have two periodic solutions that are attractive. And if you have this, you have unstable steady state and limit cycle that are growing until limit for the period of this limit cycle. This is for this here. The red one is the curve that I come back. It's like yes, because here we can put alpha less than pi over 2 over r, and you have this hyperbolic curve, which is given by the red one. Alpha equals to pi over 2. Here, the axis is the delay, and here the parameter alpha. If alpha is negative, you are 0 is unstable. If you are between 0 and this curve, you have global local asymptotic stability, and if you are here, 0 is unstable. And this part, it's periodic solutions. All this part. This part is not periodic solution. Can be, I don't know, explosion, something complicated. This is two simulations to show you what in the stability region we have stability and also oscillations, because here I took the delay, we took the delay between 1 over a and pi over 2 to have in the same time oscillations and in the same time asymptotic stability. We choose alpha equals to 1, and tau is just below Yes, tau here, it's just below to have periodic solutions, and here before pi over 2, but also before 1 over e, to have in the same time oscillations and stability. And here we can see the oscillations, the periodic solutions. This result is very, very, we call it right. You can check that it's until now it's open yet. It's not proved completely. They prove near, but it's not yet proved completely because it's to prove oscillations is very, very difficult. It's more difficult. Oh, sorry, for a nonlinear equation. Of course, for this it's finished. But if you take I don't remember the exact, I think it's this one. T minus 1, 1 minus x of t, something like that. We can prove the same result because the local asymptotic stability is okay by linearization. Periodic solutions is okay by linearization. Oscillations, no. We don't have this principle of linearization. We have to, numerically, we find the same result. If you have linear system oscillates, the nonlinear system near it oscillates also, but to prove it, it's very hard. And there is no direct theory like periodic solutions and local asymptotic stability. Global stability also doesn't work. Only local stability and periodic oscillations we can have. This is for the system. I think it was proved like tau greater than, I don't remember if it's 1 over 3 or something like that. But we know that it's like this, but no one was able to prove it until now. We can prove that there is oscillations for tau alpha greater than R alpha greater than tau, and we cannot find by numerical simulation. We always have oscillations, but no one was able to prove it until now. It's still open. This is only to prove because I told you about why. I come back to the oscillations between 1 over e and pi over 2 to see also the amplitude of oscillations. This is very good also because the amplitude starts from 0. That means there is no oscillations when we are here. And when you increase beta, the amplitude of oscillations we can see go from 0 until pi over 2 and becomes periodic. Because when you beta reach here, y come to here, and we have the oscillations becomes periodic. And this is to prove this result. It's not difficult. It's we prove that beta go to, when beta go to pi over 2, we have the eigenvalue go to this this value. And when we take the other limit, we have x go to 0, and this no, sorry, here. When x go to -1, this go to -1 also. That means we have stability. And the oscillations disappear here in this point. And they disappear also in this point, but they become periodic. This figure, it's now it's like you move beta. This is the real part, and this is the imaginary part of the eigenvalue. Okay. When you are here, beta is between 0 and 1 over e. You have only negative. Let me check. No, yes, the figure, it's only to say that we are interested only on this. The real part is negative and go from -1, -2 until -1. And when you beta is reach this value, 1 over E, you have 2 eigenvalues appear, complex one. Here you have only a real one. There is no, there is something wrong in this figure. Okay, yes, I understand what. Here I talk only about what we call principal eigenvalue, the one that is the bigger one. It's real here, and it's negative, and it's dominate all the others. Okay, and when you arrive here, this real eigenvalue disappear, and 2 complex eigenvalue appear. Okay, and the real part go there, and until here you have oscillations. Until here it becomes periodic. What time? No way. There is another question that is a surprise when you study delay differential equation, because when you have this alpha when you solve the ordinary differential equation, you put x of t, and this is for t. Okay, if I take the same, I can put here to make it I will put 1. Here for t from 0, -1, 0. The question, can we solve, because I already solved this equation by steps, but I solve it only starting from 0, between 0, 1, 0, 1, 2. Can we do the same to go back in the negative part for delay differential? The answer, no. We cannot solve with the delay differential equation can be solved only on the positive way, not in the negative. We cannot go back. It's like if you have the state of your system now, you cannot know what happens in the... no, it's not exactly. You can do it, but there is a limit. You can do it maybe one interval before, not more than that. And it depends on the regularity of your solution that you observe. For example, if you have enough regularity, you can come back to the past. As you have a regularity, you can, for example, if you have initial condition like C infinite, you can go far. But if you have only continuous initial conditions, it doesn't give you enough information to know what happens in the past. This is, and you can prove it analytically. It's for ordinary differential equation, you can go. It's like maybe more comes from physics. If you have a state of the system, you know what happened, what was the state. For biology, it's difficult because as the system is follow many directions, different directions, you cannot know what how was before. This is the interpretation of solution backward in time. Can be solved backward or forward, but delay, this cannot, doesn't work. For some initial data, you can do it. You have to be very regular, have many information to come back, many regularity, if not, you cannot. And this is the explanation. Because if you want to come back to the negative part, you have to take the derivative of the initial condition also. This is why if the initial condition is not regular, you cannot do it, and you are blocked. If you put regular initial condition, you can come back and know what and go as far, but you can never go to the infinity. There is always a limit to understand how was the system before. It's like you have a population of predator prey. Now you cannot know how the many situations can bring you in the same. There is not unique possibility in the past to bring you for this situation. It's this is explanation. This is to summarize. I come back all the time because it's important to have it in mind. This equation, if alpha is negative, you have instability but not oscillations, no periodic solutions. And the first threshold, you have asymptotic stability but not oscillations. You can have some solutions oscillate, but not all of them. And between 1 over e and pi over 2, you have in the same time asymptotic stability and all solutions oscillate. And when you come to pi over 2, you have attractive limit cycle. And if you are bigger than pi over 2, this is, I don't want to talk about limit cycle because it's more complicated. It depends on many things. What we can do, it's what we can know. We have 0 is unstable steady state. Maybe if you have questions or not to go to another or comments or of course I don't want, because if you go to the literature, of course it's always like that. Start with the simple delay differential equation, and each time other people complicate, make another things, blah blah, etc. etc. I don't. Now there are many complicated. They are very complicated. Delay differential equation. It's like I will give you only one. This is now many people study this. This is what we call delay difference equation, and the delay depends on the solution. Okay, you have this is a delay, but the delay is a function of the solution, and it's very, very nice. You have many nice numerical point of view because you have chaos, you have many things. The things not can be. You have also delay differential equation where the delay depends on the time. It moves on the time. It's and you have also what we call implicit delay. You have it's a general system. You have G of U this we call minus, here I will put alpha A plus This is, we call it implicit delay because we have an ordinary differential equation, and the difference equation is not differential. And the delay is like in this part. And this has the same kind of property. This system is now very used. We call them differential difference system. Differential and difference system in the same time, coupled between differential. This is fast and this is slow. It makes system oscillate all the time. And we have also other, what we call a neutral delay differential system. You have the delay also in the derivative, not only, it's like t minus tau. Two delays like this. Also, this kind of system. Of course, we have also partial differential reaction diffusion equation with delay. And also, like Laplacian delay in time, and there is space, and very, very nice result, because it's also the delay has impact for example, traveling waves, what we call traveling waves. The delay can sometimes, you know what is traveling waves? It's a kind of system like that, and you prove that there is like a wave go in the space with some velocity, etc. And when you add delay, the delay can make slow, can change the velocity of the wave, make it slow or fast. And this is in epidemiology use it too much because it's propagation of disease, or in space to check how many times it will. And when you have delay can decrease the velocity. It's like mosquitoes that travel, but as they have to wait to make eggs, it makes like decrease their velocity, because they need to stop to put eggs and to this kind of stuff. Because before that, people don't take account the delay and have other. But now many people say no, there is like change if we put things like that. Sometimes you mean fractional derivative, you put, yes, there is many, I cannot understand to make the link between the delay in fraction. I think it's not the same, because the delay, it's fractional delay. This one, it's like adding, taking off, it's different. Yeah, it's completely different. I will show you another before to. I consider now a non-linear function like this. Okay, x prime equals to this, and I took f scalar, and I suppose that f of 0 equals to 0. It's only to have something, and I make the assumption that this function satisfies this, for example. What it's like when you multiply the sign of, because this function has this, can be this form. The product between y and f is negative. It passes here. That means it's like this. This is true. If you multiply y positive, negative, we stay negative. And here negative, positive is negative. Yes, this kind of function like tangent or positive. This, when you add this assumption for a nonlinear create oscillations for the delay differential system. This condition create oscillations. I will show you why. If I take, this is no linear case, and we can do it by hand. If I take initial condition, minus R0, I will start from t equals to 0. Okay? This I will take it. And I will put like this. Minus 1. I have initial condition here. Okay? Now I want to know what is this derivative for t equals to 0. It's like x prime of 0, okay, equals f of phi minus 1, because it's in the past. If I multiply this by x, by phi, sorry, then I have f phi minus 1 times. As I have this property, and as this here is positive, that means this is negative. Okay? This is positive. This is, as I have this property, it's negative. Okay? All the time negative. As this is positive, this is negative. I don't need to, it's negative all the time. Okay? What I want to say, this is negative, then this is negative. No, this is positive, then this is negative. That means here I have to decrease in this point, because the derivative here is negative, because this is positive. And I continue the same things as I did here, because as this positive, I can do this. And it will be all the time negative until it will pass. I can prove it until I become here. And if we take, you will see that there is like a point. If we take this one and you do the same thing as we are here in the negative part, we will increase, etc. And you will do it all the time, and you will prove that there is oscillations. This is a very simple property, give you many functions like that, give you oscillations of, there is, because of course it's easy to prove oscillations and periodic solutions, but there is one guy, Hans Otto Walter, he spent all his life to study this, and he's famous because he find many things about, he find that there is global periodic solutions, and he find the period, the amplitude, and the period amplitude is like uniform, the same. You can choose as you like the function f, you will have periodic solution with period 4, something like that, only under this condition. What we can say also for this yes, I didn't say that, but maybe it's interesting to talk about. Yes, I will. I will take the same scalar C1. I assume, and I will make linearization. For the moment, suppose that we can do it. After that, you will see that we will prove that it's true. Linearization, that means this. Okay, this I will put here minus. It's only to have something. This is the linearization of. I will prove it after. And sorry. Yes. Okay. And the characteristic equation of this this one is lambda plus this parameter. I will put beta. What do you know the implicit function theorem? All of you know. Maybe I will introduce. You will see it's very easy to understand. It's nothing complicated. The implicit function theorem tell you if you have. We want to solve this. Okay, let's say that we want to solve in real part the other one. This one is the same. It's x. We can put this. It's maybe to introduce this result, pass in one dimension. Yes. We what is the delay here? I think I didn't took the. Yes, I will not do it now. I will show you only how it works for ordinary, for in one dimension. Imagine you want to solve because it's important for here. It can be vector or it's not a problem, and we can put all things on the left and put 0. We want to solve because our characteristic equation, we have x and y can be a vector, and we have parameter that we move. It's the delay. Okay, let's start. Suppose that x is one dimension. Okay, and plot this in the curve. What we will have. Suppose that we have this. This is r and x. When we plot this equals to 0, assume that we have this. I don't know exactly, something like that. Okay, this is a curve. It's not function. Sorry, it can be circle. I don't know. It can be something like that. Okay, because x and they are together. And the idea, you want to calculate x as function of r. Where you can do it here? Someone can tell me where, in which place x is a function of r? Sorry? Here it's okay? Here it's okay, here? Because we have, yes. But we can, until, because we can take like this region, until here. Okay, suppose that here it moves like this, enter here. In this interval, you can calculate x as a function of r. Of course, you don't until here. Okay, and it's regular. Now, look this and tell me which condition we have to put on this to be able to calculate x as a solution of one parameter. What is this point? Why this point block and this one? Maybe I will remember you when you have a curve like this. In each point, you can calculate. I take this one, something like that. The derivative, partial derivative on r and partial derivative on x. And this point, what is the problem? The partial derivative on r is 0 because it's vertical. And the implicit function theorem tell you that stay between 2 points such that the partial derivative on r is not 0, and you are able to make this implicit result that you can calculate the solutions in terms of the parameter. And as then we have to avoid this. To avoid all these points equal 0, then we assume this. Each interval you have this, you can make this calculation. You can calculate the solutions in terms of the parameter. We will do it for our function to calculate the eigenvalue in terms of the delay. And we will avoid all the points that we have this problem. And that means our eigenvalue is a curve of the delay. When you move delay, they move the same way as the delay. And we avoid this because this it's not good. It makes this movement. This is what we call implicit function theorem. That means you have an implicit function and you can put it explicit. This is what in terms of the parameter, and only, of course, if you are in more than one, this one is Jacobian of the vector is determinant of Jacobian is not equal to 0. That means the matrix, Jacobian matrix, is invertible. It's the you put inside of putting this, you put the other one. And this is more than that. We have also this function is regular, has the same regularity than this function. As we have analytic function, it's I put C1. C1, it's okay. That means I can calculate also the derivative of the eigenvalue in terms of my parameter, because I have like here I have a very regular function. And sometimes after that, when you do that, you say, okay, now I can put this because my implicit function is in fact depends on r unit, of course, in this interval. And you calculate the derivative of this in r, and you put like this, and it becomes x prime r df dx plus df dr, because here it's 1 equals to 0, and you have your you can study your eigenvalue in terms of minus d over and you can know if it's they are decreasing or increasing, and follow them until they cross the imaginary axis, becomes negative, and you obtain all results using only this kind of stuffs from mathematics. Not very difficult. This is what I will show you that how we will prove that beta equals pi over 2 is the limit is half bifurcation. We'll use exactly this. Okay. I will only discuss in general case because I put many things here to make what is the difference between the existence and uniqueness of solutions for discrete delay differential equation can be established by a method of steps. Exactly, we don't know anything about delay to do this. We take ordinary. If we have discrete delay, it's okay. But if you have a more general delay differential equation, for example, distributed delay, this we need more things because you cannot do it by steps. And existence and uniqueness is more complicated, but we have some results. The general delay differential equation need to define an appropriate state space because we don't. I told you all the time the initial condition is continuous, but is it enough or not? We will show that it's enough to take initial condition continuous to have existence, uniqueness, and all things that we can have. Yes, we have blow up, also explosion, infinite time for delay, but this is very strange in comparison with the ordinary differential equation because when you solve an ordinary differential equation, in many times you cannot solve it for all the axes. I can give you, for example, this one. This one you cannot solve it forever. You are blocked by there is a limit of interval because you divide when you integrate, blah blah blah. You will have like a limit of the interval. For delay, we have worse. We have the same problem, but we have another problem. But it's not. We can solve it. We have some conditions to avoid. For ordinary differential equation, when you have in general. There is a result told you if your maximum interval of existence of the solution is limited, the solution has to explode. There is no other way. If your interval is finite, then the solution go and explode. Okay? For delay differential equation, you have the same result, but you can have this or explosion of the derivative. This never happened in ordinary differential equation, but for delay differential equation, if you take more complicated delay differential equation, it's not. I think this never happened, but can be something. I will put like this story of. You can have this. You can have this, or you can have this. The derivative explodes, not the function, but the derivative. That means the derivative becomes infinite. The limit of the derivative becomes infinite. Okay? This never happened here. For delay differential equation can happen. You can have oscillations that becomes vertical until you cannot go more than that because the derivative becomes infinite. Okay, but this never happens in. But I will talk only about blow up. The positivity, yes. as we work with application to biology, we will see that the negative and positive feedback with delay plays an important role to the positivity of the solutions. If you have a negative feedback, it's not, I don't remember which one is better than the other, but it's very quickly, we don't need to make investigation to check for positivity. There is like a genetic result that's very easy to use. And the introduction of the delay, if you have ordinary, can make the steady state stable, or sometimes it can make it unstable. You can have both. In most example, it makes the steady state unstable, but there are other examples when you put it was unstable and it becomes stable. And this is a very good result that we will comparison principles. It's like you have your delay differential system, very complicated, and the nonlinear part, you can measure it by another function. Then you can make comparison between the solution of your system, solution of another one, more easy. And this is work also, it works very well for delay differential system. Yes, this is the local, I will come back next time to, it's very easy. If you have the nonlinear function, the derivative exists and is continuous, then you have a local existence of the solutions exactly, and you have this blow up of the solution if you reach the maximum. This is why I want to talk about this, because sometimes if you make numerical simulation for delay differential, if you don't check that your interval of existence is all, you can have results, but it's not true because you didn't take account the fact that the solution maybe exists only in a small interval. All the examples that I give you, we have global existence. This is okay, but if you wrote a new examples, you have to check that there is no problem for the global existence of the solutions. That means the solution exists for all the time. Okay, maybe I will stop here and continue if you have questions or. Yes.